last segment for this week. I know this was a lot. I appreciate your efforts working through it. This definition of potential energy, I want to unpack it a little bit. Suppose, as written, it includes all the conservative forces. It includes gravity, elastic force, whatever. Suppose we're only talking about a particular potential energy. That the potential energy associated with some conservative force is the negative of the work done by that conservative force. On average, the work done should be the force times the little bit of displacement. Let's say that we're moving in one direction. Let's say that the force and the displacement are in the same direction. Let's keep things really just nice for now. So yeah, there's a dot product, but magnitude, cosine of the angle. If the angle between them is 0, then this is all we need. So this is, I guess, in order that the force and the displacement, the x displacement, are in the same direction, we must be talking about the x component of the force, I guess. So like, we divide both sides by delta x, and I guess we're talking like on average, over some interval, over some displacement, the potential energy changes by a certain amount, and divide that by the displacement over which that change occurred, and that's roughly equal to, I guess we could call this the average force in a certain sense. I mean, it's not average in time, it's average in position, but roughly it's a, an approximation for the force that acts during this displacement. But what if we let the displacement become infinitesimally small? I mean, the smaller the displacement is, the less of an approximation it is. If delta x is infinitesimal, it's not an approximation at all because the force is roughly constant. I mean, it's a point, right? I mean, it's the 2 points infinitesimally close together. The change of f of x on that interval is so small, this would be an exact equal sign, not an approximation. There might be one of these statements for the y direction and the z direction as well, that there might be a y component of the force that is the negative derivative of the position, the negative of the potential energy function. Derivative of the potential energy function with respect to y or with respect to z. And the force, the vector force, would be the fx in I hat plus f sub y j hat plus, so this, so there is some conservative force that has some x component according to this, and some y component, and and some z component k hat, but the fx is negative derivative of u with respect to x I hat minus du dy j hat minus du dz k hat. Now, in order for the potential energy to be a function that has value, that has derivatives, rates of change in all three directions, it has to be a function, generally speaking, of all three. So this is, we're taking the derivative of some function that's actually a multi-valued function, right? This is some potential energy function that is a function of x and y and z, generally speaking. But we're only taking a derivative with respect to x. What do we do with the other two? The dot product lets us know that we don't care. I only care about the component that is parallel to, which means what? As far as derivatives are concerned, I treat them like nothing. I treat them like constants. I treat them like they aren't actually changing. I pretend like the potential energy function isn't a function of x and y and z that can change, but only a function of x. And just leave y and z alone. Pretend that they are just parameters, just like g or mu or something. They just hang out. We can take derivatives around them almost. The kind of derivative we're talking about is called a partial derivative. We take a derivative of u only with respect to part of its variables, leaving the others constant. Instead of a lowercase d, I'll use this sort of curly symbol del. It's a d, but instead of having the little squared off bottom, it's all sort of swoopy. Sort of like a backwards letter 6. Did I just say letter 6? Woof. I think it's time to be done. We could define if we wanted to. A vector operator. Called the gradient operator. The gradient operator is the thing that says do the partial with respect to x and then put that in the I hat. Do the partial with respect to y, do the partial with respect to j, put them in the j, or put them in the y and z directions, and make it take those derivatives of what? Whatever comes after. So gradient operator equals partial with respect to x as allocated to I hat direction, partial with respect to y as allocated to the j, and partial with respect to z allocated to the k. There's nothing here to differentiate, partial or otherwise, until we write gradient operator acting on the potential energy function. then we know what we're taking the partials of. So this gradient symbol is a vector calculus instruction. It's an instruction to do a thing upon the variable that comes next. Gradient, like imagine yourself on terrain, and the gradient of the terrain is the slope. If you look this way, what's the slope? If you look that way, what's the slope? If you look this way, what's the slope? Imagine that you are on a three-dimensional surface instead of a four-dimensional surface, or instead of a two-dimensional surface. Imagine that you're standing in a room, and at every point in the room, there's a little thermometer measuring the temperature. If you look in the X direction, the temperature changes a particular way. If you look in the Y direction, the temperature changes maybe a different way. If you look in the Z direction, the temperature changes maybe a particular way. The combination of them all together tells you where the thermal energy is going. What is the temperature gradient in the room? And if I had some thermal energy, some sort of thing that could ride on top of, that could be moved according to temperature differences, it would move in this direction. It would move according to where the terrain is steepest, right? If that way is kind of downhill and that way is kind of downhill, and that's true because this way, diagonally between them, there's like a giant hole. A thing released in this terrain is going to roll that way towards the giant hole because there's some force to the X, some force to the Y, and together that thing is going to be pushed that way according to the gradient of the terrain. So we have everywhere in the room a potential energy function. And we look this way, we look this way, we look this way. Say, how does it change? Where is it steepest? If we ask for that steepness as vector, in which direction are we pushed? We are pushed so that we go downhill. We're pushed to decrease the potential, which makes a lot of sense. If we increase the potential energy of a system, gravity, elastic force, will always try to decrease it back, to put it back to the way it was. These conservative forces always try to decrease the value of the potential energy. Those are the things that I need to say in video for this week. We will explore all these things in greater detail and with an eye towards application. What does it all mean as we go through the week? Worksheets, recitations, labs. Let me know if you have questions about these videos. There's lots of office hour appointments available. Look for mine, look for Sean's as well. And thanks, everybody.